Welcome back. This is video 14A. We're going to look at modeling the sample proportion. So let's look at an example. At Cecil College, let's say that we are charged with the task of estimating the proportion of students who smoke cigarettes. So recently the national percentage is holding at 20%, but at Cecil College we don't know that that's what it would be. We really don't know what it would be until we collected some data. So let's say that we have a hunch that at Cecil College a greater percentage of our students are smokers when compared with the national figure. And let's just say that our hunch is based on anecdotal evidence. It seems like we see a lot of people smoking. Cecil County is rural, and there are a lot of cigarette butts in the doorways and in the parking lot. Now, to really determine whether our hunch is valid, again, we're going to have to collect some data. So first, let's also define what we're going to call a smoker. Let's say that if you have smoked at least one cigarette during the last 7 days, that's going to be our definition of what a smoker is. So that's just how we're going to define it. You might think it's something else, but that's what we're going to go with. The true proportion of students that smoke, student smokers at Cecil College, we don't know what that is, right? Unless we went and talked to every single student at the college, we don't know what that is. So this is unknown. We don't know what that is. The value that describes the population. If we knew what that value was, values that describe the population are called parameters. I always like to remember population starts with P, parameter starts with P. So when you have a value that describes something about a population, it's called a parameter. And for this example, the population would be all Cecil students. We'll estimate that perhaps there's around 2,500 Cecil students, so we'll say the population is all 2,500 or so Cecil students. And if we had any values that described something about all the students, they would be parameters. Now, pretty difficult to get some information on every single student at the college. So we decide that at Cecil College, we'll just take a sample of students. So we decide to sample 100 students. And the way we go about that, we decide to randomly select names from the spring semester's registration records. And then we're going to poll students when they pay for their classes. So we're going to randomly select 100 students. The students that get selected, they get polled when they pay for their classes. Once we collect the data, we can calculate the sample proportion. Now this value comes from a sample. The sample proportion, the symbol we'll use for this is a statistic because it's collected from a sample, not the whole population. We'll call that P with a hat on top of it, P hat. And we'll get that from those 100 student responses. Okay, so let's say that it turns out we sample 100 students and we have 30 smokers. Take 30 over 100, that's 30% in our sample are smokers. So let's think about that. What would happen to the 30% if we throw back the 100 students and we do it all over again? If we did it all over again, do you think we'd get exactly 30 smokers in a sample of 100 students? Probably not, right? Okay, so then we do it again. We throw all the students back in, take another random sample of students. Out of this 100 students, do you think, again, we'd get 30 smokers or however many we got the second time? Probably not, right? Those values are probably going to vary. So let's say that each time we record the value of the sample proportion of smokers. So perhaps we do this over and over again. And each time we write down, hey, in this sample it was 30%, in this sample it was 25%, this time it was 32%, and we record all those values. This lesson, lesson 14, investigates the theoretical distribution if you looked at every possible sample of 100 students and looked at the sample proportion. So what would happen if you did this over and over and over again? We will never do this. This would take forever to do. But theoretically, we're going to talk about what would happen. It also, another reason why you don't do this is it costs money, takes a lot of time to collect samples. So typically we'll collect one sample, but you need to keep in mind that you only have one sample, and if you did this again, you'd probably get different results. So we'll talk about how those samples will vary. Let's draw a picture and talk some more about how the sample will vary. So I want to draw a picture of what the population is in the context of this smoking problem and what the sample is. So I'm going to get a clean picture. So let me make a big circle. I'll call this the population. So our population is all Cecil College students. For sample size, we use a capital letter N, and we're going to say there's about 2,500 Cecil students. So this is all 2,500 Cecil students. And what we're really interested in is what percentage of Cecil students are smokers. Again, that's a value from the population, and so for that, that's a parameter. We'll use the lowercase letter p to describe that. So p is going to be the percentage of all Cecil students that are smokers. Now imagine if we're crazy and we looked at everybody, all 2,500 students, and we asked them if they smoked or not. We could find this out. It would take an enormous amount of time. It could be expensive to collect that. But if we did get that proportion, that percentage, that's for everybody, so that's not going to change. It's a fixed value. Now we don't know what that is. So P is a fixed value, but we don't know what it is. So just a note here about P. P is fixed, it doesn't change, but it's also unknown. Okay, so here's our sample. Again, the population size and the population proportion are parameters with regards to that. This is what we really care about. That's difficult to get, so instead of looking at the whole population, we're going to collect a sample of information. So let's say we take a random sample. And so over here's our sample. We use the lowercase letter n to denote the size of a sample. So we said we were going to sample 100 students. So these are the 100 students that we sample. And out of those 100 students, we again count up how many are smokers, and we record that percentage. This is from the sample. We call this p hat. And the first time we did this, first I'll just say this is the sample proportion. We got 30% in the sample that smoked. So let's say for this sample, this is 30%. You know, just for reference in the future, we took the number of smokers that we had out of the total number in our sample, and that's how we came up with that number. Hopefully that's pretty obvious. Some comments on this, though. That's if we sampled one time, which that's all we'll, in practice, be doing. But what if theoretically we took those 100 students, dumped them back in the population, randomly took another sample of 100 students and looked at the sample proportion? What would happen again? So we could do this again. We could take a second sample. We could take a third sample. So what would happen if we sampled over and over again? Those sample proportions are not going to be the same for this sample and this sample and this sample. So those sample proportions will change from sample to sample. Now imagine if, and we don't know this, But if the true proportion of smokers at Cecil was, let's say, 25%, how likely do you think it would be to get a sample of 100 students where 90% of them were smokers? A random sample, not a biased sample. Probably not very likely, right? So one of the things that we're going to talk about in this lesson is, yes, those values will vary, but what's the likelihood that you get certain values for that sample proportion? Is that a likely value, or is the likelihood of getting a value like that kind of small? So we'll talk about how they vary. Although they vary, though, some values are going to be more likely to occur than others. And so we're going to look at the distribution of those p-hat values and see which values are likely and which ones are not so likely. So we'll talk about that in the subsequent lessons in this Unit 14. I think that's it for this one.